Welcome to integrating powers of tangent and secant. So the goal here is we want to integrate things of the form the integral of tangent to the m of x times secant to the n of x dx. Turns out some of these we can fairly quickly use substitution for, and others are a little more complicated. So it's useful to break this particular type of integral into 4 cases. The first case will be the case where n is even. And in particular, we're going to do n is even and n greater than 0. So if we have n even, then we can set n equal to 2k. And so we have the integral of tangent to the m of x times secant to the 2k of x dx. Now, keep in mind that if we wanted to use u substitution, we would either like a integral, or we would either like a secant squared around, since that's derivative of tangent, or we would like a secant tangent around, since that's derivative of secant. So in this case, we're going to force a secant squared x dx for u sub. So the way we are going to do that is we will rewrite this integral as the integral of tangent to the m of x times secant to the 2k minus 2 of x times secant squared of x dx. This is precisely the same thing as the integral of tangent to the m of x times secant squared of x raised to the k minus 1 times secant squared of x dx. I need to give myself a little bit more room. At this point, we are going to use the fact that we have 1 plus tangent squared x is equal to secant squared x. Or in other words, secant squared of x is equal to, oh, sorry, I have that already. We're using the fact that 1 plus tangent squared of x is equal to secant squared of x. So this becomes the integral of tangent to the m of x times 1 plus tangent squared of x. That entire 1 plus tangent squared of x is raised to the k minus 1, then times secant squared of x dx. At this point, we'll use u sub. We'll set u equal to tangent of x. Then we get that our du is precisely that secant squared of x dx that we had forced. And so we are looking at the integral of u to the m times 1 plus u squared. That entire 1 plus u squared is raised to the k minus 1, and then du. And then at this point, we expand and integrate. Again, so this is a useful way to force a u substitution by essentially turning all the secants into tangent except for one set of secant squared, just to force that u substitution that we wanted. Next up is our other possible u substitution. So in the case where m is odd, we can also apply u sub. So if m is odd, and n is greater than or equal to 1, so n is not equal to 0, then we will go ahead and set m equal to 2k plus 1. So we have the integral of tangent to the m of x times secant to the n of x dx is equal to the integral of tangent to the 2k plus 1 of x times secant to the n of x dx. At this point, we are going to force the other possible u substitution here. So we are going to force u sub with u equaling secant of x. Doing so means we need du equals secant x tan x to fall out. So we are going to peel off one tangent and one secant to force this format. So we are looking at the integral of tangent of x, tangent to the 2k of x times secant to the n minus 1 of x, and then we peeled off one tangent of x and one secant of x dx. Then we need to convert all of our tangents to secants. So we will use the fact that tan squared of x plus 1 is equal to secant squared of x. Or in other words, tan squared of x is equal to secant squared of x minus 1. So we are looking at, we need to force our tan squared. We are looking at the integral of tan squared of x. That whole tan squared then raised to the k times secant to the n minus 1 of x times tangent of x secant of x dx. That tan squared, of course, can be rewritten as secant squared of x minus 1. That entire secant squared of x minus 1 is now raised to the k times secant to the n minus 1 of x times tangent of x times secant of x dx. We will now apply u sub. We will set u equal to secant of x. Our du is that desired secant of x tan x dx. And so we wind up looking at an integral of u squared minus 1 raised to the k times u to the n minus 1 du. At this point, again, we expand and integrate. Now we get to the case that does not fall in either of these. So the first option was for n even, and then second was for m odd. So now we're going to do the combined case of n odd and m even. So for n odd and m even, we're going to play a slightly annoying game here. These ones are not so pleasant. M even, we will set m equal to 2k. Right? So we have the integral of tangent to the m of x, secant to the n of x dx is equal to the integral of tangent to the 2k of x, secant to the n of x dx. We will rewrite that tangent to the 2k of x as tangent squared of x, the entire tangent squared, then raised to the k, times secant to the n of x dx. At this point, we will then use the fact that tan squared of x is equal to secant squared of x minus 1. And so we have, this is the integral of secant squared of x minus 1, that entire secant squared of x minus 1 being raised to the k, times secant to the n of x dx. At this point, we will expand. There is no pleasant u substitution falling out. Then we will use integration by parts. With dv equal to secant squared x dx. I will do the most basic example of this that we could possibly have, which is just secant cubed in a future video, and then I will also do a more complicated case. Our last case is the case where m is even and n equals 0. So again, let's go ahead and set m equal to 2k. So we are looking at the integral of tangent to the 2k of x dx. There is no secant, no power on the secant here, or 0 power on the secant. What we are going to do is we are going to essentially peel off a secant square, or a tan squared. So we are going to rewrite this as the integral of tangent to the 2k minus 2 of x times tangent squared of x dx. Then we will use the fact that tan squared of x is secant squared of x minus 1. So we are looking at the integral of tangent to the 2k minus 2 of x times secant squared of x minus 1 dx. Splitting this into two integrals, we are looking at tangent to the 2k minus 2 of x times secant squared of x dx minus the integral of tangent to the 2k minus 2 of x dx. This first integral falls nicely into our case 1. So this first integral we can evaluate using case 1. The second integral we can evaluate by reapplying case 4 with this reduced power. So we are going to evaluate using case 4 again. So the annoying thing with case 3 and case 4 is you wind up having to keep doing more and more and more integrals as you slowly reduce the powers. But this is a technique we can use. It is possible to evaluate no matter how high that power on tangent is. You may just have to run the same tricks over and over and over again. So in the next video, we'll look at some case 1 and case 2 examples, the more basic cases. And then after that, we will get into the more complicated case 3 and case 4 examples.